Okay, welcome to Math 331 problem solving. We are at the final two classes of the semester, getting ready for the Putnam. So this is lecture 35. And what I want to do today is I want to talk about the number 2024 and then do some Putnam A1 problems as time permits. One of the, I think, requirements when you write a math competition is to use the year somehow. And frequently the year is just used as a number. Its properties typically don't matter, but it's always a good idea to have some knowledge of properties of the number. So I think the only Putnam problem that we haven't discussed yet was an algebra problem about some ring R. If there's time and interest later today, we can talk about how might you tackle a problem like this. The first idea is, do you think there actually exists? Well, I guess just while we're waiting, just very quickly, do you think there exists a ring that has this property? That's different than the question that's being asked. The question that's being asked is, let R be a ring not necessarily with identity, which means, oh, okay, so if you know abstract algebra, this restricts a little bit of what you're looking at. Suppose there exists a non-zero element X of R satisfying the following, prove or disprove there exists an element Y of R satisfying Y squared equals Y. And again, the condition was X to the fourth plus X equals 2X cubed. Do you think there exists at least one ring with this property? And you don't even have to know what a ring is. Do you think there exists at least one ring with this property? Sorry? Yeah, almost surely, right? And what might that ring have? What kind of ring might have this? Well, it says, let R be a ring not necessarily with identity. Suppose that there exists a non-zero element. What kind of ring might this be? What kind of property might your example have? What's the keyword to focus on? Or I would focus on the phrase not necessarily with identity. So maybe this is trivial for every ring that has an identity, right? If you have an identity element, can you find an element Y such that Y squared equals Y? Yeah, that's not that hard, right? Take the identity element. So when they say not necessarily with identity, the only interesting case is going to be when R does not have an identity. Now, you could have non-trivial elements that are not the identity, such that Y squared equals Y. And it might be interesting to see, can you find other elements like that? But if you're going to try to build intuition, I would start looking at rings that don't have identities in terms of trying to attack a problem like this. Okay.
So, not necessarily with identity. So you have a ring that has a multiplicative identity.
So then the question is, what's the definition of a ring? And this is why this is not necessarily a great Putnam problem, because if you haven't done abstract algebra, what do you do for a problem like this? So how many of you have taken abstract algebra? Okay, for the record, I've never taken it. I've taught it, but I've never taken it. Long story. And so I don't think this is being recorded. Never mind. I think this is a wonderful problem. I think it was great that it was given without any definitions of what a ring is, that you should know what a ring is when you're coming in to take the Putnam exam. But it wouldn't be a bad idea to just quickly remind people. So if you haven't seen rings before, this is what we mean. These are the properties. And rings have both multiplicative and additive structures. And so when you say not necessarily with identity, this is typically with a multiplicative identity that's being talked about. It has to have an identity. And in fact, that's why they say there exists a non-zero element, because the other identity that you could use is zero. And if you think about what's going on, this is looking at Y squared minus Y equals 0, or just factoring Y minus the identity, if there is a multiplicative identity, equals 0. And this might give you an idea of where you might be able to find some other elements that might work. Now, you need to have a multiplicative identity if you want to write something like this. But you might think of maybe something like a clock group. But of course, if it's going to be multiplicative, it does have to have an identity. Okay. So I don't want to go into too much of this, especially if nobody here has taken abstract algebra, but just wanted to talk very briefly about my first thoughts when I see something like this. Always, always, always gather data. And where should I be gathering data? When it says not necessarily with identity, to me, it's not just not necessarily means that's where you have to look. That if you have an identity, it's almost surely going to be trivial. It's still not a bad idea to quickly see, hey, can I resolve the case if there is an identity? Because maybe I can then be lucky and then I don't have to do anything. And it's a really easy problem. Unlikely on the Putnam, possible on an easier math competition. Right. So one of my associates sent a nice email. I sent this on to you about properties of the number 2024. And so you should know immediately that 2024 is not prime. If you do not know this, I don't know how you got into 331, but 2024 is clearly not prime. What is its factorization? It's not too bad to go because we can quickly see that 8 goes into it. And then the number, when you divide by 8, you'll see is a multiple by 11. You'll be left with 13. So it's good to know that it factors, it has 3 distinct factors. And then there's a bunch of different properties. And so you will notice things such as Cunningham number, binomial coefficient, betrothed pair, Harshad number, palindrome, unprimable, untouchable, tetrahedral, pernicious, polite, arithmetic, apocalyptic, amenable. There's so many different names that people can create. It makes something a little bit more fun when you give it a name, and then you can maybe convince people to study amicable numbers and whatnot. And I would very carefully pasted this in so everything is hyperlinked so that when you look at the PDF of the slides, if you just click on anything, you get to the appropriate quantities. The question becomes, which of these things are interesting? You can give anything a name in mathematics. Is it an interesting object to study? And then there were a few more properties, wasteful, odious, and whatnot. So I want to list a couple of natural questions. Oops, gotta switch back to pen. Good questions to always ask. And the first, do examples exist? If yes, infinitely many. If yes, growth rate. How many do you have up to a given point? And so if there's only a finite number of them, it may not be as interesting. If there's infinitely many, everybody here, again, must know what a prime number is. I'm assuming everybody knows that. If you don't know that, please just nod your head so that I feel our educational system is not horrendous. Do you know what Carmichael numbers are? So Carmichael numbers have similar properties than primes in a certain regard, in that only primes and Carmichael numbers, let's say, there's a certain test to see whether or not a number is composite. If the number is composite, it will almost always tell you that the number is composite. But occasionally, there will be some numbers that cannot determine if it's composite or not. And those numbers are the primes and the Carmichaels. There are not that many Carmichael numbers, but unfortunately, because they exist, you can't use this test for primality. And so then the big question is, how many Carmichael numbers are there? And it turns out there's far, far more primes than Carmichael numbers, so that if you run the test and it doesn't return composite, it's almost surely prime. It's not a proof that it's prime, but it gives you confidence. And so you want to know, how many examples are there? How quickly are they growing as a rate? You can define anything you want. Carmichael numbers turn out to be a good thing to study. As an aside, as you get older, you need to know bad math jokes. Do you all know the joke that every positive integer is interesting? You know the joke? All right, so I will prove to you every positive integer is interesting. One I think we can all agree is interesting because it's the unit, multiplicative unit identity, yes. 2 is interesting, it's the only even prime. And now we just proceed by induction. Imagine you have a positive integer which is not interesting. Then that's the first positive integer that's not interesting. That's a really interesting property. So every positive integer is interesting. So again, for a lot of what we're going to do today, we're going to be looking at things like odious, wasteful, betrothed, untouchable, all these different quantities. I think the one I chose was polite number, because I'm from Boston. We have a reputation for being polite people, and so I thought I would talk a little bit about polite numbers today. So a number is polite if it can be written as a sum of consecutive natural numbers. So for instance, 2024 is the sum of 77 plus 78 plus 79 all the way up to plus 99. So I don't expect everybody to be as familiar with politeness as a native Bostonian, but now that you're familiar with it, you can start asking the questions. Do polite numbers exist? What do you think? Yeah, this is basically, are you awake right now? I just said 2024 is polite. So assuming that we haven't done an algebraic mistake, we know that polite numbers exist. Do there exist infinitely many polite numbers? Yes. How can you generate infinitely many polite numbers?
Just take the previous point.
Perfect. So now we know the answer to the first one, polite numbers exist. There's an infinite amount of politeness in the world. Great. But relative to all the integers, what fraction of numbers are polite up to a given size? Do you think a positive percent of all numbers are polite? Do you think a majority of numbers are maybe New York? Unpolite.
Oh. So if it's a sum of consecutive natural numbers, does that mean just having one natural number doesn't count as a?
So that's a good question. So this is where it is so easy to have a bad definition. What's the definition of a prime? A lot of people say a number is prime if it's only divisible by 1 and itself. If you use that as your definition, what's wrong? Then 1 would be prime. And we don't want 1 to be prime because then we lose unique factorization. So we say a number is prime if it has exactly 2 distinct divisors, 1 in itself. And with that definition, 1 is excluded from being prime. So you have to be careful. So when you look at this, since it can be written as a sum of consecutive naturals, so as soon as you say sum, do you consider one element by itself a sum?
Well,
exactly. Right. Well, it depends. For some things, you would want to allow that.
It also depends on the numbers. If you put 1, you could do like 0 plus 1.
So you could do 0 plus 1. And so this is why they're saying consecutive naturals, because 0 is not considered.
Like 0 plus 2, but they wouldn't be consecutive.
But they wouldn't be consecutive. So if you, and then this argument as to whether or not 0, I think, should be considered a natural. So all that 0 would give you would be that 1 would be polite. But so it's an important question as to maybe we want a polite number to have at least 2 summons.
I also feel like 0 would not be good just because then every number is.
No, because it has to be consecutive.
Oh, I see.
It has to be consecutive. So 0 would only help with 1. So, again, this is how you do research. You have a bunch of standard questions that you ask, and whenever you see anything, you start asking them. So when I see polite, the first, do polite numbers exist? Do infinitely many? And a lot of times you have trivial proofs for infinitely many. I can construct this nice chain, just take a polite number, add the next summoned, add the next summoned, add the next summoned. But that's maybe a little bit wasteful in terms of how large of a gap I get between my next number. And so you can ask, if I just did this, would I get a positive percent? Can I prove a positive percent of numbers are polite? Or if not, how many numbers do I lose? Does the limit exist? Is there some kind of nice function that describes, up to x, how many numbers? Is it maybe x to the 1/2? Is it x to the 1 minus delta? Is it x over log x? These are great questions to ask. What is the growth rate? And this is one of the things I want you to get out of this class. Whenever you see something that's already been done, ask, how can you push this forward? And a lot of times, if you just get into the habit of asking good questions, eventually you hit pay dirt. So a lot of it is, being lucky, being in the right place at the right time, asking questions. But if you get in the habit of always asking these questions, you're more likely to take advantage of being in the right place. All right. I assume everybody knows what this is. Yeah, probably helps also that says Pascal's triangle, but I don't think it's really needed. I'm not entirely sure why it's colored the way it is, but with a little bit of work, you could probably figure it out. I think I figured out why it's colored the way it is. Any thoughts? So which numbers are in yellow, which numbers are in white? Good. Multiples of 3 are in white and non-multiples of 3 are in yellow. Normally I see Pascal's triangle shaded by even or odd. This one is multiple of 3, non-multiple of 3. And you can see, some kind of fractal structure emerging. This is the advantage of. And then, of course, this region is similar to that region, similar to that region, and just, continuing onward. Okay. So everybody has seen Pascal's triangle. There was something about 2024 that intrigued me. Here we go. It was this one. 2024 is a non-trivial binomial coefficient being equal to 24 choose 3. I did not know that. Had no need to know that, before looking this up. And so, is every number a binomial coefficient? Is every integer somewhere in Pascal's triangle? So if I give you numbers 1776, 24601, 1701.
Yeah, I think it is.
Okay. Can you tell me where I might find 1701?
I think we have like the 1701 throw.
Yes! Right?
It's really lazy, but it should work.
So here's a trivial proof that any positive integer is in Pascal's triangle. Just look at, n choose 1, and that gives you n. Right? So we know the outside rows are all 1s. And then the next row is all the integer n's.
That's a non-trivial.
Yeah. Yeah. The first non-trivial binomial number that you meet is? So look at the picture. Give me a non-trivial binomial coefficient. 6. 6 is not n choose 1 or n choose n minus 1 by symmetry. 6 is 4 choose 2. So there exists at least one non-trivial binomial coefficient, 6. Have we gone far enough to see 2024? No, because they said it was 24 choose 3s. We actually haven't gone far enough to see it. So this then leads to an interesting question. We know that there exists at least one non-trivial binomial coefficient? Do there exist infinitely many? So exists a non-trivial binomial coefficient. 6, which is 4, choose 2. Do you think there exists infinitely many? Yes. Can you give me a string of numbers that will be infinitely many distinct binomial coefficients?
I guess you could just do n choose 2 for n starting at 4 and going to infinity.
Okay, so you could do n choose 2, or you could do 2n choose n. There's lots of ways you can do it. So we know that there's many, we know that there's infinitely many. And the last is, what is the growth rate? What is the growth rate? Again, these are the 3 natural questions that you ask whenever you see something. There's actually a 4th question you might ask is, I'll maybe go back and put in the 4th question. Can you give an explicit formula? That's if you really want to show off. Can you actually enumerate which the objects are? We can't really do that for the primes. We can count them, but so again, this is how you generate questions. You start off with something simple, it's a non-trivial. Do you think that a positive percent of numbers are going to be non-trivial binomial coefficients, or do you think in the limit almost all numbers are not? So if you look at this, we have some huge numbers like 24,310, but we know much smaller numbers like 2024, which we haven't seen yet, will emerge. So the question is, how are the gaps filled in? Because just because we've gone to the 17th row doesn't mean that if we go to later rows, everything is going to be larger than what we've seen. We're going to be filling in some gaps. So how many of these gaps can be filled in? So this is what I want you to be thinking about, in future classes as you're doing things, not just in math, but just in anything. Just how far can I push this? How can I use these ideas? So, we can't do this on a Putnam exam, but since this is not a Putnam exam, I just wrote a dinky code, and I decided to have a little bit of fun and not use Mathematica's in-house binomial coefficient calculator. I calculated the binomial coefficients myself. For a problem like this going to such a small height, I don't really need to do this. But I just wanted to demonstrate my programming skills and try to get some street cred, because sometimes when you go farther up, it actually makes a difference. And if you're doing the same thing again and again and again, there's an opportunity for efficiency. So this was a nice opportunity to talk about that again. So I have a little thing over here at the end, and I wrote basically n choose k is n factorial over k factorial n minus k factorial. And if you do a little bit of algebra, it's the same as n choose k plus 1 times n minus 1 over k plus 1. And I just rearrange things a little bit. Why is this useful? Well, if n is large, if I already know n choose k, I don't want to compute n choose k plus 1 from scratch and multiplying everything again. So I might as well take advantage of the fact that I know the previous number. Should I multiply by n minus k and then divide by k plus 1? Should I divide by k plus 1 and then multiply by n minus k, or does it not matter? Which do you think? Should I do the multiplication first or the division first, or does it not matter? There is a right answer for this problem. And you've got a 1 in 3 shot. Can you think of any dangers that might happen with a multiplication or division?
Is it possible that n choose k plus 1 is just not divisible by?
So maybe it's not divisible by k plus 1, but k plus 1 divides that times n minus k. So it would be great to do some experiments and see, could that ever happen? We know that it has to be an integer. So we know that when you finish the entire operation, but maybe if you divide it by k plus 1 first, you might get a fraction. There could be a rounding error if your numbers are huge. And then when you multiply by n minus k, there could be an issue. So I would always keep things integers. I would do the multiplication first and then do the division. But as a nice exercise, you can ask, do you ever have a situation? If I had to guess, I would say, I'm sure I could find a situation, but I'm not extremely confident about that statement. I'd want to play with it a little bit, gather some data. I think that's a great thing to check. Will k plus 1 always divide? Probably not. And you can probably find an example pretty quickly. So what I did is I looked at the first 25 rows or 26 rows of Pascal's triangle. I might have been a computer science. Well, we know that we don't have to start worrying until we get to the third row, or actually the fourth row. The fourth row is the first row that can have a non-trivial binomial coefficient, because we don't include anything in the ones or the ones after that. So I don't care if I'm starting at the 0th row or the first row, because I'm starting beyond there. So I looked at the first, I think 25, I looked up to row 25, starting from row 4. And I got a list of all of the non-trivial binomial coefficients. And here's the list. And you can see that we have gone far enough that we do get, 2024, it does emerge. You see that there's a lot of gaps. And the question is, how are these filled in? Do you think it's going to be a positive percent? Looking at this data. As you go further and further down Pascal's triangle, do you think you'll be able to fill in stuff from higher rows? Yes, if the row is just a little bit above, sure. But what if the row is significantly above? Do you think the numbers in Pascal's triangle will just get too big to fill up? And so that's the question. So that's what I wanted to talk about today, is just how would you attack problems like this, inspired by just seeing silly facts about 2024, and just try to show you the thought process. So I have not thought about these, so I'm going to just attack them with the first instincts. So, so recall n is polite if n is equal to k plus 1 plus ... plus k plus maybe L minus 1 with L greater than or equal to 2.
Isn't it that, or maybe I was misreading the comment, but I thought I said that it was polite because you could do that 3 different ways.
No, it says it's a polite number that has 3 different representations.
Okay.
So just because you're polite doesn't mean that there exists only one way of proving that you're polite. You could be polite in different ways. And that becomes an interesting question. You can say a number is too polite if it has 2 different polite representations. It's 3 polite. And what can you say about the fraction of numbers that are 2 polite, 3 polite, 4 polite? I would tend to think that the more politeness you impose on a number, the harder it's going to be. I'm just thinking of real world examples. I know a lot of people who are very polite to their superiors and not so much to the people who work for them. And so it would be very interesting to then ask, what percent of polite numbers are too polite? So we want to try to figure out what percent of integers less than or equal to x are polite. So any thoughts about how we would attack this?
You guys would start by picking like x equals 10 or something, or just seeing like what we get, just gather some data.
Okay, so one is gather data. And for this, it's computers. So I'm in some negotiations trying to convince people that we need a lot more, machine learning and AI, instruction, not just here, but throughout the math community. When you read, did I send the article about AI from Caltech? No, okay, I'll send that after class today. Just in terms of what these programming environments can do is they can handle so many of these grunt work steps and just gather the data, analyze it, and sometimes even go through logical steps. So one is to gather some data and get a feel for which numbers are polite. Now, to see if a number is polite, you would have to look at differences of triangular numbers. So Tn is the nth triangular number. It's 1 plus 2 plus ... plus n, which is n plus 1 over 2. We've proven that several times. The easiest way to see the proof of that is Tn is also n plus n minus 1 plus ... plus 1. And then if you add, you get 2Tn is n plus 1 plus ... plus n plus 1, a total of n times, which is then just going to be n plus 1 n times. Therefore, Tn is equal to n plus 1 over 2. This is the famous Gauss sum of first powers. So we know a triangle number is the sum of the first n consecutive numbers. So a polite number, so if m is polite, then m is equal to Tn minus, I don't know, maybe T, let's not use m. I'll use P for polite. So if P is polite, then I can write it as a difference of two triangle numbers. And that gives me some hope maybe of trying to analyze something like this. So we are now looking at Tn minus Tm, or n plus 1 over 2 minus m plus 1 over 2. And what do we know about n and m? Good. And that's all we know. So n is greater than or equal to m plus 1. So eventually, if I give you an m, n is going to be so large that Tn minus Tm is going to be bigger than a fixed amount. So if I want to look at numbers up to a certain size, what can I look at? How big is, say, Tn minus 1? So that's going to be n plus 1 over 2 minus n minus 1 n over 2. Yes? So that's going to be n halves, and then we're going to have n plus 1 minus n minus 1. Is that just going to be 2? Yes? Makes sense, right? How do you get from Tn minus 1 to Tn? You just added n. So it's nice that the algebra checks. So if I fix the smaller number, then I know my next one has to be at least a certain amount bigger than it. So the question is, if I want to have a number like 7, do I have to worry about infinitely many pairs of n and m, or are there only finitely many pairs I need to check? So to see if 7 is polite, check finite or infinitely many pairs.
should be
Only finite.
Yeah.
So if they grew at a different rate, but they're growing quadratically. And so when I look at the difference is going linearly. So there's only finitely many things that I'm going to need to check. So I can check everything with m equals 1, m equals 2, m equals 3, all the way up to m equals 7. And then once m equals 8, we know that there's nothing to check. So okay to check m less than equal to 7. And for each one of them, do I have infinitely many n to check? No, because once n is sufficiently large, the difference is clearly going to be more than 7. So it's at least a finite problem to tell if a number is polite.
in general, M has to be at least half, right? Or no more than half of p plus 1. Because if you divide p by, or whatever the number is, if you divide it by 2,
Right.
and add two numbers in that, two consecutive numbers in that range, which is the minimum for triangle number two sums, then you'll have the number back at least.
Okay, so your claim is m is was it at least or at most?
I think I need to think more about it.
Okay.
But basically, like, there's only so many n's or m's that we need to check.
I'll leave it, some kind of general claim.
So I think it has to be at most the number over 2 plus 1. And
Okay.
that's probably generous.
Right. No, and again, that's what you want to do. You want to start off with a really bad bound that's easy to do, and then try to see if you can improve it. And again, for something like this, the better bound you have, the tighter you have, the faster you can be for searching. And so now the question is, how many different numbers will we get as we vary n and m? And so let's say we want Tn minus Tm to be less than or equal to x with n equals m plus k and k is greater than or equal to 1. So one of the things you could do is you could just look at how many pairs do I have that will satisfy this, and assume every pair gives a number that's different from every other pair. And that would be an upper bound for how many polite numbers there are. So if m equals 1, n goes from 2 to how high can m go? So how large of an n could we take? So we need, n plus 1 over 2 minus 1 to be less than or equal to x. Yeah, so basically n times n plus 1 is less than or equal to 2x plus 1. Who wants to use the quadratic formula? No one wants to use the quadratic formula. So we could do n squared is less than or equal to n plus 1 less than or equal to 2x plus 1. Thus, n is less than or equal to the square root of 2x plus 1. And that would be one way to get an upper bound. Here's another nice trick. Could do n times n plus 1 is n plus 1/2 squared minus 1/4. Right? So you would get n plus 1/2 squared is less than equal to 2x plus 1 plus 1/4. So n plus 1/2 squared less than equal to 2x. Then we're going to have plus 2 plus 1/4 plus 9/4. So you would get n would be less than equal to the square root of 2x plus 9/4 minus 1/2. So you could do a little bit better than 2x plus 2, maybe. Actually, these should not be less than equal to, right? Well, I guess they are still less than equal to because they inherited the less than equal to from before. But this really is n times n plus 1. We're not losing anything like that. So when you're doing arguments like this, you always want to keep track of how much we're losing. So this shows if m equals 1, n goes from 2 to approximately the square root of 2x. Just trying to get a rough sense. That's pretty good in terms of size. Right? We know roughly that the number of n's that work is going to be growing at a rate of square root of x. And that's when m equals 1. What do we try next? M equals 2. And so now, if m equals 2, then n goes from 3 to what? All right, do we really want to go through and do the calculation for 3, 4, 5, 6? Can we just do the general case? So the general case, if m equals m, which is always true, right? Then n goes from m plus 1 to what? So we would need n plus 1 over 2 minus m plus 1 over 2 to be less than or equal to x. So n plus 1 minus m plus 1 is less than or equal to 2x. Actually, I'm going to use the trick now of replacing n plus 1 with n plus 1/2 squared minus 1/4. Why is that going to be a good thing to do? Because I can do the same thing for the m's, right? And get that as m plus 1/2 squared minus 1/4 less than or equal to 2x. So all of a sudden, rather than having these horrible terms n plus 1, m plus 1, I can replace it with n plus 1/2 squared and m plus 1/2 squared. And the 1/4 are going to cancel. So we get n plus 1/2 squared is less than or equal to 2x plus m plus 1/2 squared. So n is going to be less than or equal to the square root of 2x plus m plus 1/2 squared minus 1/2. So we see that does this look reasonable? So the larger m is, the larger x can be. Does that make sense? Yeah. But now what's interesting is if m is large, then remember we have the square root of 2x plus m plus 1/2 squared. That's going to be at least m plus 1/2. So this is reasonable that, you always want to worry about, we need n to be greater than m. Well, this is at least m plus 1/2. Because we're taking the square root of m plus 1/2 squared. So then the range, so the number of n is going to be roughly the square root of 2x plus m plus 1/2 squared minus m. All right, I have the minus 1/2 minus m, okay, up to plus or minus 1. So for a given value of m, that's how many I have. How large can m be? And 1 less than equal to m. What's the largest m we can take such that Tn minus Tm is at most x? So if you think about it, I think the largest m can be maybe is when Tn is adding just one more term. So that new term should just be, I think, x. So I think the largest m could be is maybe x minus 1. Or is it like the square root? I'm sorry, it's whatever index corresponds to the triangle numbers about x. Right. So you want the last term in your sum to be x minus 1. Does that make sense? So we want 1 plus dot 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 plus k to be m, and k should be x minus 1, right?
Yeah.
So m would be x minus 1 times x over 2. So we would need to sum this quantity for m in this range. So I'll let you think about that for, and again, we may discover that when we do this, that this is not useful. This would give us the number of, polite pairs, but multiple pairs could give you the same polite number. In fact, we know that that's the case because we know 2024 is 3 polite. So this is going to just be an upper bound. When you look at how many m's there are and you look at this range, the question is, what can you say about how large that sum is? Is that sum going to be larger than x? If it's larger than x, then this is completely useless.
Do we actually know what percent of numbers?
I don't. And so this is one of the nice things about teaching a class like this is I'm not allowed to prepare too much for the lecture. I can prepare for next lecture. I can prepare for Wednesday's the follow-up. But as of now, I don't know what the answer is. I don't know any results about polite. I have deliberately not looked it up.
Okay, so I feel like it would be quite difficult to answer that question just because it's kind of like a subset of the additive analog.
Well, there are often techniques. The question is, how elementarily can you attack a question like this? This is the most naive approach possible. I'm trying to get really a rough bound on pairs. I'm going to assume every pair is disjoint from every other pair, no numbers repeated, and just try to get something like that. Bad assumption.
The number of pairs like both monotone and bounded. Whenever I hear the word bounded, I think about the monotone convergence theorem, and I start thinking about like bounds and limits and stuff.
Right. I mean,
so,
the number of pairs that can generate a number at most x is bounded.
Yeah.
Yes. And that's why we can do a sum like this.
Yeah.
But we need to evaluate that. So now, if m is very large, then the 2x doesn't really matter that much, and the number of terms is going to be very small. But we're taking a huge number of terms. M is going up to basically x squared. And to me, because m is going up to x squared, there's just too many damn pairs. Even if there was only one choice of pair for each choice of m, since m is going up to x squared, that's far more than x. This is not going to work. But what this might be telling you is that some numbers have to be multiply polite, maybe in a growing number of ways. Just by the pigeonhole principle. If we have this many pairs and we only have x numbers, well, then some number, wow, is there going to be some number less than x that's polite at least x times? We might have just proven that there is some number up to x that's at least x polite. And one of the reasons this problem is tricky is because m and n can go beyond x. So you can go a little bit further and have some of these subtractions happen. We might have also made a small mistake and whatnot. So I'll let you think about this for Wednesday's class. And then also think about, do you have any idea about what the growth rate might be for the number of non-trivial binomial coefficients? It looks like there's a very small number here. We have explicit formulas for the binomial coefficients. We did have an explicit formula for the polite numbers. There's a lot of similarities between these two problems. Just because you have an explicit formula does not mean it's tractable. I might show you on Wednesday, because it's the final class trying to just do fun stuff and put everything together. There's an explicit formula that will tell you whether or not a number can be written, an even number can be written as the sum of two primes. That's wonderful. This is the Goldbach problem. In fact, it's an integral. If you can solve this integral, you can determine whether or not this number is the sum of two primes. We don't know how to do this integral. Just because I've written it down doesn't mean it's doable. So just because I'm writing down these questions, there might be other ways of looking at it. This idea of trying to attack by counting the number of pairs, that might not be the right way of looking at things. What I really have is, maybe it kind of looks like a hyperbola. The n plus 1/2 squared minus n plus 1/2 squared less than or equal to something, that looks a lot like a hyperbola with just different values. And maybe I just want to count how many integer points are there on hyperbolas. And this starts introducing me to various stuff in number theory. All right, so this is a good place to stop.